Hello, everybody. We're going to wait for a couple of minutes so all participants can log in, and then we're going to start with our session today. '87 participants. Ooh, we're good. 90. Maybe a few more seconds and then we'll start. All right. So welcome everybody to the Multiscale Model Applications and Evaluations session at CMAS conference this year. I am Marina Astitha from the University of Connecticut. I'm co-chairing this with Kristen Foley. She will take the lead after a couple of slides. I want to welcome our panelists and our participants and thank everybody for their contributions. Really interesting talks today. Kristen, do you want to move to the next slide just to introduce? I'll have 16 presentations from senior scientists all the way to PhD students. We're very proud of the work we've done. And we've seen Charmaine is one. Hi, Charmaine. Masture, Wan Ying, Shi Ying, James, Tugsi, Christina, and of course I don't pronounce everything correctly, sorry about that. Lucas, Christian, Shannon, Yukui, Thalia, Alejandra, Mike, Heather, Nash, Pradeepa. So whatever questions that might come up, please use the Q&A toolbox so we can moderate the questions and assign them to each panelist. And Kristen, that's your turn.
Okay, great. Thank you so much. Well, before we jump into the Q&A sessions and let all our panelists give a little 1-minute introduction, I was just going to take a minute to give a quick recap. Marina and I were really impressed with the breadth and depth of the modeling applications in this session. There's a lot of diversity across these 16 talks. I counted at least 10 different numerical models used for meteorological, air quality, and hydrology modeling. Many of the talks focus on US and Canada, but we also have applications in Colombia, Iran, and Pearl River Delta, and an evaluation of hemispheric CAMX. So I encourage you to listen to those if you haven't already. The timescales also cover the entire spectrum with a deep dive into a multi-day dust episodes, all the way up to multi-decadal analysis of on-road air pollution. So this session also covers an impressive range of what I would consider advanced modeling evaluation methods. So you're going to hear about how source apportionment can be used for the contribution analysis of ozone and nitrogen deposition, how adjoint modeling can be used for estimating monetary benefit per ton of NOx emission reduction from aviation emissions, how data fusion and machine learning methods can be used to estimate important water quality indicators, mainly nitrogen and sulfur deposition and chlorophyll A. And then we also saw multiple applications of satellite data. There's really many examples of how it's being used for evaluation of biases in emissions inputs and boundary conditions for regional air quality models. So I think that these talks really represent a cross-section of the state of the science and environmental modeling right now. So we're really struck by how the researchers that you're going to hear from today are leveraging and combining really disparate data sources, whether this means multiple ground networks or satellite data, multimedia modeling, land use and roadway data. So I think it's exciting to see how the different data sources are coming together. And as a statistician, I really like seeing examples of how statistical models can be used to tie all those data sources together. You also see that throughout just how application driven these studies are. So while the modeling techniques themselves are really impressive and interesting to learn about in their own right, all of the presenters have very compelling air or water quality management questions that they're using their modeling tools to try and answer. So again, if you haven't watched all the presentations, I encourage you to go back this afternoon and listen to them. We did have 12 questions come in ahead of time. So we're going to give our presenters a chance to answer those. We're going to have everybody come on and give you a quick 1-minute summary. And so as they're doing that, please go ahead and use that question and answer box and submit additional questions. And then the only other reminder is to, for the presenters to please remember to unmute yourself when it's your turn and then go back to mute when you're done. So we're gonna get started because we have 16 presenters to get through. So I'm gonna start with Sharmin Akhtar from the University of Connecticut, who presented on modeling the contribution of long-range transport to nitrogen deposition in the US hydrological regions.
Hello, everyone. Good afternoon. So my topic is modeling the contribution of long-range transport to nitrogen deposition in US hydrological regions. So in my work, I evaluate and model the different major source regions contribution to nitrogen deposition in United States. So we use comprehensive air quality model with extension CMAS version 6.0, along with particulate source apportionment technology PSET to track different source regions contribution to nitrogen deposition in US watershed regions based on hydrologic unit code HAG2. So what we did, we modeled different nitrogen containing species and their deposition, such as dry and wet deposition on different watershed. And it will evaluate impacts of nitrogen on different watershed based on the HAG2 regions. And it will help the environmental regulators and guide them to set different rules and regulation to protect the environment and also the human health for this nitrogen deposition that is occurring through this excess amount of nitrogen. And we evaluate different species based on the particular source apportionment technology and their impacts on the environment here. And that's all.
Very good, thank you. Marina, I'll just let you chime in if there are questions. Otherwise, I'm gonna keep going through the presenters.
There is one question from Kara for Sharmin. Is there an explanation for the high deposition due to long-range transport from California to the lower Mississippi region when California itself did not experience high deposition?
Yeah, that's a good question, actually. So I am assuming due to the high elevation of different point emissions that could lead the higher range of transport due to different chemical reactions that is occurring in the atmosphere that could lead this high deposition from California to lower Mississippi regions here.
Great, thank you. So our next speaker is Mostufa Almeri from the University of Tehran, and she presented on investigating the influences of dust storms on precipitation in Iran using WRF-Chem.
Hello, everyone. In my research, I tried to find the relationship between the dust storm periods and the precipitation spatial temporal changes. And we run the version 3.6.1 of the WRF model. And with the chemical evaluating the two scenarios, we found out that storms have impacts on the precipitation in Iran. And we find the correlations between between all the meteorological metrics and unfortunately, our least correlation was for the wind speed and wind direction, and I think that it was because of the exact question that said about HVC, that is hybrid hybrid vertical coordination, that is in the version 4 of the WordCamp, and in my thesis, our latest version was 3.9, and in that version it was only for the real data, but in the version 4 it is for all data, real and ideal data, and I'm working on it for my paper, my next paper, and I'm working on it.
Oh, that's great. Okay. It sounds like you already answered the question, but that's kind of forward-looking for moving to a different WRF version. Was there a question, an additional question, Marina?
No, no question in the Q&A.
Great. Well, thank you so much, Ms. Tuhra. We're going to move to Cheng-Wan Ying from Hong Kong University of Science and Technology, who presented on source apportionment of ozone under different synoptic patterns in the Pearl River Delta region.
Hello, everyone. It's a great pleasure for me to be here. In my work, the CMAS modeling system with the ozone source apportionment technology module was applied to analyze the influence of particular synaptic patterns, including sea high pressure, equalizing pressure field, and subtropic high pressure. Our results show that the concentration of ozone increased under 3 meteorological conditions in the Pearl River Delta region. In the equalizing pressure field, the contribution of superregional transport increased by 6.1%. With the effect of subtropic high pressure, the local contribution increased significantly, especially in Jiangmen and Shenzhen. It indicates that the collaborative emission control measurements should be strengthened with the surrounding area. Thank you very much for your kind attention. If you have any question, please free to contact me.
Thank you.
We don't have an additional question right now, but questions might come in later on, so we'll make sure to pass them on.
Yeah, that sounds good. Going to move on to Cheng-Si from Sonoma Technology. Is Cheng-Si online at this point? Because otherwise we can circle back. He was giving an update on the TDEP model fusion method for estimating dry and wet deposition.
He is not online, Kristen. I think we should.
No, that's fine. If you see him come on, then we can easily come back. Thanks.
I will.
Next is James East from the EPA, who presented on implementing satellite NI2 data assimilation in CMAC for identifying emissions biases and improving regional boundary conditions.
Okay, thanks, Kristen. So in this work, we used a 3D VAR chemical data assimilation method to assimilate OMI NO2 columns into CMAC over the continental US. And the goal is to be able to use the updated composition assimilation to get some estimates of NOx emissions biases and provide updated NOx emissions estimates. And so the first part of the work was to present a case study using the OMI satellite over the United States. And the second part of the work, I showed some preliminary results that we've been preparing using the TROPOMI satellite, which has higher resolution over the hemispheric domain, so rather than just the continental United States.
And so there were two questions that were submitted, James. I think you've seen these. One was when you were talking about your TROPOMI analysis, you referred to a large uncertainty. And so they ask if you could talk a little bit about what that is and what are the next steps to make this a more routine and robust option for model evaluation.
Yeah, thanks for the question. So I'd say the sort of the things that I was referring to regarding uncertainties for the TROPOMI assimilation, three things in particular. One was the background error covariance, which helps distribute the analysis increment around the domain and determine how much impact the data assimilation actually has on the model simulation. And a lot of these background error covariances are developed for meteorological simulations. And so we develop our own on our domain for a chemical data assimilation for NO2. And so there's some uncertainty in that estimate, and we're hoping to refine that. I'd say there's also some uncertainty in the averaging kernel. So we're using NO2 vertical shape factors from the native shape factors that come with Tropomi. And then we're assimilating that into hemispheric CMAC. So I think there's been some previous work that's shown that data assimilation sort of can be improved if you use the shape factors and the averaging kernel based on the model that you're assimilating into rather than the native values. And the last thing I'll say is, for this work, we're using 2018 representative day emissions. And so it's almost, you could think of it like a climatological emissions data set. I think if we were to get, the question asked specifically about routine and robust evaluation. So to do that, we would want maybe a more accurate data set, which those are available. We're just using the sort of climatological one for this.
Okay, great. Thanks, Jane. The next one asked about some specific slides. It says, it appears the CMAC NO2 is approximately 2 times larger than OMI, yet the NOx emissions changes after the assimilation appear to be very small, on the order of a few %. So if the averaging kernel is accounting for in a later step, this may explain this discrepancy, or maybe this is related to spatial resolution differences between satellite and model. Do you have any further thoughts on this? And so I think this is one of the slides they were asking about.
Yeah, so this slide, and thanks for including this, Kristen. This slide is the OMI, just the OMI data taken directly from the satellite. And then the next slide is the CMAX NO2 column. And so you can see they don't really compare quite one-to-one. And I think that the point in the question about the averaging kernel was a good point. We aren't accounting for the OMI averaging kernel or the OMI scattering weights in the CMAC column just for these figures. In the actual data assimilation, we do account for the OMI scattering weight. So these two figures themselves, I think, are more just illustrative of the two columns and the data that's available. And then just the last thing I'll mention is to make this figure, I didn't filter out the days when retrievals are available. So for any one grid cell, there's only about 1 to 2 retrievals available per day. And so that's what you're seeing with OMI, but for CMAC, this is an average over all of the time steps throughout the modeling period. So to get a more accurate comparison, I would need to have filtered out for the days. But thanks for the question, I appreciate it.
That's good, thank you.
We have one more for James. How did you choose the BC matrix in the GSI 3D VAR? Did you look at PM as well?
Yeah, thank you for the question. We didn't look at any covariances with other species, like PM, or with any meteorological variables. And to develop the background error covariance, we are using an NCAR program called GenB that's used a lot with the WRF data assimilation system. And so we use a perturbed run. We basically use two different model runs, and it develops a very model and domain specific background error covariance for NO2 over our domain. So I hope that answered the question, but thanks for those good questions.
Thanks, James.
Yeah, thank you, James. Our next speaker is Touche Erdem from Carleton University, who presented on estimating societal damages from aviation emissions in Canada.
Thank you, Kristen. Hello, here is Touche. We used CMAC adjoint to quantify location-specific marginal damages for emissions associated with aviation in Canada. And this study aims to create a database of location-specific marginal benefit information for aircraft emissions and related aviation emissions, such as ground surface vehicles and airport traffic. The adjoint approach attributes monetized national health burden to sources at individual locations. For instance, preliminary results we obtained are benefit per ton values for NOx and PM2.5 under 900-meter where LTO takes place, and 3-kilometer altitude that is one of the aircraft cruising altitude, and 10-kilometer that's a common cruising altitude. And two main takeaway preliminary results I can say are the largest estimated benefit per tons of reducing PM2.5 comes from Toronto Pearson International Airport, and the largest health benefit estimates are attributed to landing takeoff that contributes to a quarter of the benefits. Thank you.
Very good summary. Are there a question?
No questions so far.
We'll have a chance to circle back. I'm going to go ahead and move to Christina Chang. Christina is from the University of Connecticut and presented on the sensitivity of machine learning based model to predict chlorophyll using multimedia modeling environmental predictors.
Thank you. Hi, everyone. My name is Christina, and in the video presentation, I talk about how we use different multimedia modeling numerical prediction models and use machine learning to assess algal blooms using chlorophyll A as a proxy. So the output models that we're using is EPIC for agricultural variables, CMAC for end deposition variables, WRF for meteorological variables, and VIC for hydrological variables. And we're predicting chlorophyll A concentrations in the United States part of Lake Erie for 11 years from 2002 to 2012. And aside from predicting chlorophyll A concentrations, we also aim to identify those important environmental variables that may lead to algal blooms. And another thing that we did was to examine the sensitivity of the model by varying different EPIC, CMAC, WRF, and VIC output variables. So I highly recommend you watch the video for more information about our findings. Thank you.
Great, thank you, Christina. There was a question that was submitted. It said, do you think it would be possible to get access to wastewater discharges from industrial and municipal sources to add to your model? This would seem to have the potential to be a very important explanatory variable that it can improve your estimates, particularly for the very high chlorophyll A value.
Yes, so thank you for the question. To answer this question, there's already wastewater discharge data available for from EPA's National Pollutant Database. So in there, wastewater facilities have to report the data, which includes nitrogen and phosphorus, in order to be compliant with the EPA. And it is possible to include these point sources into our model, but we have to have consistent data. So we're doing an 11-year period for now. So we would have to have 11-year period data for the wastewater facilities. And in addition, we are using explanatory variables that are coming from different numerical prediction models. So these are variables that we can actually predict. There's currently no model that predicts wastewater discharge variables. So we are not using that for now, but we could definitely use the observations of those wastewater facilities, those measurements to try to run the model and predict a smaller time period if they have, fewer years.
Oh, great. Thank you.
Yeah, thank you.
Next speaker is Lucas Henneman from George Mason University, who spoke on or presented on 4 decades of United States on-road air pollution, spatial temporal trends assessed by ground-based monitors, air quality models, and satellites.
Great, thanks, Kristen. Thanks, everyone. So we were motivated by 2 things for this work. The first is that in epidemiology and environmental justice, you'll often see these location-based proxy metrics used in place of exposure to traffic-related air pollution. And then the second, we saw an opportunity to evaluate how well different air quality modeling products or satellites capture the trends that we see in these long-term observation records that we have in the US. So Actually, Kristen, I think the next slide you have the statistical model. Thanks. So we applied this model, and there's a lot here, but there are sort of 4 important things to take away. The first is that beta naught term. So we looked at the average concentration in the first year. The beta R term is the relationship between concentration and roadiness or road proximity at that base year. Beta 1 is the concentration time relationship, and then beta 2 is the interaction between road proximity and time. So we applied this model to observations at ground monitors. We also applied it to all the different modeling products we looked at. So I think one of the questions is on the next slide about what all these coefficients mean. So on the x-axis here, on the left are our coefficients from observations. Then we have 2 CMAC products, 12 kilometer and 36 kilometer, a merged satellite product, and then just the OMI values. And we're comparing how these things vary in space and in time. So that, and I'll note, so the question was about how these are presented. So since this is a very dynamic evaluation of these models, we're not looking at the raw concentrations here. They're actually the average over the time period is presented in that top row in the very small text. These are presented as a % of that average concentration. And the big takeaway here is that both of the CMAC products actually capture all of these relationships fairly well. In the satellite products actually show a little bit more sensitivity to the time trend across 2002 to 2010, and then even show a little bit more sensitivity of road proximity on that time trend. That's the 1-minute takeaway there. And then the second question was about the next slide. So we use this framework to sort of get at a policy question of whether states adopted light duty vehicle standards, whether they adopted California's light duty vehicle standards, emission standards. And so these are the same coefficients. So the top left are the intercepts. You can see in 2010, the average NO2 concentrations were highest in California states and other states that adopted the standards, a little bit lower in the states that didn't adopt the standards. Now, the question was about the lower right-hand panel, which is the relationship between road proximity and the time trend. So in California, it actually had a pretty strong relationship between road proximity and the time trend, versus in the yes and no states, you saw a very similar relationship. You'd expect that the yes states would be similar to California since they adopted the regulations. I think the reason that they're so similar goes back to the bottom left panel, which is the relationship between concentration and road proximity. The yes states actually have a very low relationship, or a weaker relationship, between concentrations and road proximity than all the other states, which I think explains why they have a weaker relationship than California with the time trend and road proximity.
Okay, great. Thank you. I know that was a pretty detailed question to try and answer quickly. So I appreciate that, Lucas. I think
we have one more for Lucas.
I think maybe, well, let's save that just so we can get to the presenters and then see if we have
okay. Got it.
No, thanks. So our next presenter is Christian Hoger from the EPA, who presented on impacts of differences in land use characterization and dry deposition schemes on ACME4 CMAC simulations.
Thank you. So in this study, we are applying the CMAC model in 2 and 4 different configurations to contribute to the model intercomparison effort under the 4th phase of ACME. an international collaboration between North American and European modeling groups. And the focus of this phase is to look at deposition processes in an attempt to better understand differences in model performance across different modeling systems. So for the CMAX simulations, we are contributing to this augmented comparison effort. We're looking at the impacts of both land use differences and then also components that contribute to dry deposition on the model dry deposition. So the land use differences we're looking at are using NLCD40 or MODIS land use, and we're looking at two CMAC configurations. The M3 dry and stage dry deposition schemes are available. And what's really new in this intercomparison effort is that we're not just looking at dry deposition velocities and how they relate to differences in concentrations and fluxes, but that we're breaking down the dry deposition velocities into their components by land use and by deposition pathways. That means by stomatal, cuticular, soil, and lower canopy pathways. So when applying that concept both to the CMAC runs here and for the overall augmented comparison effort, that allows us to do a more diagnostic evaluation and interpretation of model-to-model differences, and to look at ecosystems impacts, since the different deposition pathways will have different implications. For the CMAC runs we're looking at specifically, we do find that using the MODIS land use scheme generally yields consistently lower ozone during the summer, or actually throughout the year, than the NLCD40 due to a different distribution of land use classes with higher deposition velocity overall in the MODIS setup. And comparing M3 dry to stage, we do see generally higher summer ozone and lower winter ozone in stage compared to M3 dry. And a driving reason for that appears to be the fact that when we look at the deposition pathways, there's a greater contribution from stomatal and cuticular pathways in the M3 dry scheme versus the stage scheme. So you have more of a impact on the seasonal variations in those dry depositions. So yes, that's the high level summary, and there's a lot more detail in the recorded presentation.
Great, thank you, Christian. Do you have a question for now, Marina?
No, we don't.
Okay. Our next speaker is Shannon Phillips, also from the EPA, who presented on changes in ozone production chemistry across the US between 2007 and 2016, an integrated modeling assessment.
Thanks, Kristen. So this is an effort that I'm co-leading with Heather Simon, who's also at the EPA and speaking later in this session. The motivation for this work is, as most people in this audience probably know, ozone precursor emissions, and particularly anthropogenic NOx, have been declining pretty substantially for most of the country over the last decade or so. And these drastic changes in precursor emissions have implications for ozone formation chemistry and consequently the responsiveness of ozone pollution to precursor emissions in different areas. And so it's important for us to understand both in kind of the available ambient monitoring data, what these shifts in chemistry look like for different areas. And it's also important to make sure that we have confidence in the modeling tools that we use frequently for regulatory and policy assessments, that we have confidence that those modeling tools are effectively capturing those same patterns that we're seeing in the observations. And so in this work, we use both ambient monitor data and the CMAX model implemented with HDDM to characterize ozone formation regimes in 2 years, about a decade apart, 2007 and 2016, both through a day of week analysis at individual monitor locations, and then also using the CAMX HDDM results nationally for all grid cells in the CONUS domain. And what we're finding is that even though there are a few urban areas that are continuing to exhibit kind of transitional behavior, in general, there's a trend both in the monitor data and the modeling results towards NOx limitation for most of the country. And this is consistent with our understanding of the emissions trajectories and also consistent with what other studies in the literature are finding.
Great, thank you, Shannon. And there was a question that was submitted. It said several recent epidemiological studies report health impacts using an annually averaged ozone metric. Have you looked into ozone sensitivity outside the traditional ozone season, specifically cold months? And if so, are there notable changes between 2007 and 2016? And what are possible implications of annually averaged ozone metrics and ozone reduction efforts?
Yeah, thanks for the question. Heather might have thoughts on this as well, but I could just take a stab. So we haven't looked in detail at seasonal comparisons yet. We have the data to do that. So that's a good suggestion. I think, you know, obviously the current construction of the standard for the NAAQS is still focusing on those high ozone days in the summer period. So that's where a lot of our efforts continue to go. But we are aware of discussions related to kind of examining ozone exposure across the whole year. And that's actually one reason why for this most recent round of the NAAQS review for ozone, we did do a full year of modeling just to begin to work towards that effort. Yeah, I think it's a good suggestion and something we can dig into with the data that we have. There's obviously some probably more challenges for the model during the winter months compared to summer, just like there's challenges representing nighttime ozone compared to daytime, but it's a good point and it's something we can and will dig into. So thanks.
Thank you, Shannon. Our next speaker is Uche Lee from the University of Connecticut, who presented on source contributions to ozone in Connecticut.
Hello, everyone. I'm Uche Lee. My presentation is about the source contribution to ozone in Connecticut. Connecticut has been continued to receive balanced grades for ozone according to the American Land Association, the State of the Air report. So I use CMAS version 6.50 and its tools, OSET and also DDM. And we also use CMAS version 5.3.1 and its tool ISAM to study the different sources contribution and also sources sensitivity to ozone in Connecticut. And the sources including initial condition, boundary condition, and 9 selected sources in the New York, Connecticut, and New Jersey tri-state metropolitan, and also the unapportioned sources around the US domain. And our finding in this study is that boundary condition and unapportioned sources contribute the most to ozone in Connecticut. The overall contribution from the 9 selected sources was fairly low in Connecticut, and the contribution of boundary condition remains constant, while the contribution of other sources and 9 selected sources made up much of the change that lead to high ozone episode. Thank you.
Thank you. Our next speaker is Delia Alejandra Montego Barreto from the University of Los Andes. Her presentation was on atmospheric emission reduction scenarios in Colombia, assessing the sectoral contributions to aerosol, NOx, and ozone population-weighted concentration.
Thanks. Hello, everyone. In this work, we use the WorkChem chemical transport model to evaluate the impact of different economic sectors on air quality in Colombia and its capital, Bogota. Three nested domains located in northern or South America were used with resolution of 27 kilometers and 9 kilometers and 3 kilometers and cells of 120 per 120 by second domain, 126 per 126, and the third domain 132 per 132 with 41 vertical levels. We found that in Colombia, the sectors with the greatest attribution to PM 2.5 concentrations are mobile and industrial sources. For the city of Bogota, it was found that the paved on unpaved roads and the renovation of heavy vehicles are the scenarios that would cause the greatest reduction in air pollution in the city.
Thank you so much. And there were 2 questions that came in. One is about figure 10, or figure on your slide 10 that I'll go to in just a minute. And then the second one is, what would you say are the most significant uncertainties for air quality modeling in Colombia and in Bogota, either for your work specifically or for modeling that region in general? So I don't know which question you want to answer first. The other one was about what is shown in this map on this slide.
Thank for your question. and answering yes, that is correct. The graph to the right on the slide 10 shows the sector with largest contribution to PM 2.5 emission in each cell. Regarding uncertainties, probably the largest uncertainty is the emissions themselves. And there are only detailed emission inventories for 5 series in Colombia. Bogotá is one of them, with aggregate 1 kilometer per 1 kilometer emission inventory. This, however, for Bogotá, we need to better describe what is happening in the southwestern area of the city. And for our simulation, we use emission factors developed for other countries. It would be convenient to decrease the uncertainties on the emission factors. It requires measuring them as well as in the chemical expression of particles. Thanks.
Great, thank you, Alejandra. Our next speaker is Mike Moran from Environment and Climate Change Canada. Is Mike online? He gave a presentation on ongoing multi-model evaluation of operational air quality forecasts over North America. And so was comparing forecasts across different models. And we might give him a chance to circle back if he joins us later.
Mike
was on.
Mike is on. I'm sorry, Mike. You have to unmute.
Mike, you're muted, Mike.
I'm afraid we can't hear you. Oh.
How is that?
Got it. Thanks, Mike.
Okay. As you can see, I'm not a Zoom aficionado yet. Okay. So I'm giving a presentation on a new effort to compare, to share and compare operational air quality forecasts for North America. There are 3 operational forecast centers that are participating. So Environment and Climate Change Canada, NOAA, and the European Center for Medium Range Forecasting. We started our evaluation with January 2017 forecasts. And in the presentation, I described the air quality forecast systems, recent updates that have been made to these systems, the measurement data that are used, the evaluation system that is used, and then I show some sample results for the second quarter of this year, including monthly factor of 2 scores, correlation coefficient, and mean fractional bias.
That was a perfect summary. You did have a question come in asking if you had any insight on why the Canadian models, RAQ, DPS, and Fireworks tend to greatly underpredict PM 2.5 in both seasons, while the other models tend to overpredict. And this was the slide, one of the slides it was referencing.
Yeah, and that was turned out, it's actually a very interesting question. So the PM 2.5 forecasts are given in the bottom row of this slide. And the color coding is such, the green line is the Environment Canada forecast. The black line is the observed values, and the blue and red lines are the other 2 systems that were part of the comparison. And from this figure, it's, oh, I'm sorry, Kristen, did you have the previous slide? No, okay. So the question is because for the April to June period, there was a definite under forecast. And the purpose of this slide is to show that for the previous wintertime period, December through February, it was to the contrary, that the Environment Canada model was actually very close to the observations. So there's a strong seasonal dependence in the model, in the system performance. One difference between the Environment Canada model and the other 2 models is that we do not, in this version of the model, include wildfire emissions. That's not so important in the spring, but becomes increasingly important in the summer. We do, I think, have a need to work on our biogenic secondary organic aerosol predictions. Our springtime biogenic emissions are a bit too low. So that's one place that we think we can raise our values for the summer. We've also updated the numerical solver that we're using for our sedimentation scheme, and that has the effect of actually reducing the degree of sedimentation removal. And we're also going to try looking at our wet removal. So there's a number of process representations that could be contributing that we are following up on.
Okay,
so
great.
Thank you for the question.
Yeah, I apologize. You're right. I dropped the slide that actually showed the under prediction, but I appreciate you adding this one to show that seasonal dependence. Was there an additional question that came in, Marina?
There is one, yeah, for Mike, a follow-up question. What are the potential reasons for the underestimation of PM 2.5?
Clearly, the treatment of emissions, but then also the treatment of chemical transformation processes to form secondary organics and secondary inorganics, and then the removal processes. So there's a number of places in the mass balance where there could be reasons for under predictions or for over predictions.
Great, thank you for addressing those questions. Our next speaker is Heather Simon from the EPA, who presented on evaluation of CMAC and CAMX ozone and PM 2.5 using the 2016 V1 emissions inventory.
Thanks, Kristen. So we're in the process in the Office of Air Quality Planning and Standards of developing our 2016 regulatory modeling platform. So as part of that, we're taking the most recent emissions inventory, which is the 2016 V1 that was developed as part of a large collaborative effort with states and EPA. And we ran those through both the CMAC 531 model as well as CAMX version 7 beta 6, I think was the version we used. And we've done a series of different sensitivity runs to test out different options and inputs. And I showed model evaluation results for ozone, nitrate, and sulfate. One of the features we saw for ozone was that with our base simulation, which used a hemispheric CMAC boundary conditions, we were under predicting in the springtime and the winter. But if you switch that in our sensitivity with using geoschem, some of those under predictions in the spring got better, but then it led to more over predictions in the summer. So the geoschem ozone boundary conditions just tended to be higher overall. So it made performance better where ozone was too low and worse where ozone was good or too high. And then another interesting finding we saw with the nitrate was, and folks may not be surprised about this, with CMAC, our base simulation didn't have bidirectional flux, and we tested out both the stage and the M3 dry flux, and seemed that with CMAC, using either of those bidi options made nitrate performance a lot better. But with CAMX, turning on the bidi seemed to lead to some substantial nitrate over predictions.
Great, thank you, Heather, for that summary. There was a question that came in that said, have you or are you planning to compare the model output to ozone sondes? In particular, it'd be interesting to see how the vertical structure of ozone is simulated on the worst air quality days, as opposed to some of the work presented in other talks, which compare ozone sondes over longer timeframes.
So we haven't done any ozone sonde comparisons for these regional simulations. Baron Henderson presented last year at CMAS the hemispheric boundary conditions that we actually used in these simulations. He had done some ozone sonde comparisons, I think, for those hemispheric runs, but we have not looked at that at this point for the regional runs.
Okay, thank you. Our next speaker is Nash Skipper from Georgia Tech, who presented on estimating US background ozone levels using data fusion.
Thanks, Kristen. So for the short summary of the talk, we use simulated ozone from CMAC along with ozone observations to develop a data fusion method to try to improve agreement of US background ozone estimates, which estimates can vary quite a bit depending on which model is used to estimate it and even how the model is set up. So to remind people, US background ozone is ozone that would be present if there were 0 US anthropogenic emissions, and the background ozone can be a pretty significant portion of the total ozone at certain times and in certain locations. So we also looked at how biases in US background ozone and anthropogenic ozone components were distributed spatially and temporally. And in the end, we did get improved agreement across 4 different cases that we looked at after applying this data fusion bias adjustment method. So I think it was a success in that sense.
Great, thanks, Nash. There were 2 questions that came in. One is about a specific slide that I can show, slide 9. Why the anthropogenic ozone is so much lower than the background mixing ratios, and why is it sometimes negative? That's the first question, referring to this slide.
Yeah, so one reason can be that the anthropogenic ozone is pretty low during the winter. So since you don't have so much photochemistry going on to drive the ozone production, so that sort of brings down the annual average, which is what is shown here. So if you're looking at, say, if it was averaged across like ozone season or summer, for example, you would expect to see higher anthropogenic than what is shown here. Another thing to consider is that the split between the background and the anthropogenic ozone will usually look different on the high ozone days. So on the high ozone days, or on the highest ozone days, usually the anthropogenic component is a lot higher than what's shown here. So like, especially if I like filtered it to only show the average across days that were greater than 70 ppb, like the anthropogenic ozone will probably be driving most of the exceedances still. As for the second part about why it's the anthropogenic portion is sometimes negative, for the annual average, there's very few areas where the annual average of anthropogenic ozone was negative. So those are kind of outliers. It's only like a couple grid cells where that happened, but it can definitely be negative on specific days though, if the conditions are right. So I mean, what it means physically for the anthropogenic ozone to be negative is that the background ozone is greater than the total ozone or the base case ozone. So that can happen. Usually when it happened, it was during winter when ozone was pretty low and in areas where there's high anthropogenic NOx emissions. So that would tend to deplete the ozone, but you don't really have the photochemistry to produce the ozone. So really, like, the ozone destruction is overwhelming the production in high NOx areas and causing the background to be suppressed. So I'll end it there.
Yeah, thank you. That's good. There's a second question that said, have you considered a cross-validation evaluation to evaluate your adjusted ozone values against observations that have not been used in the regression estimation step?
Yeah, I didn't show it in the presentation, but we did do a cross-validation for the paper. So we looked at a like 10-fold cross-validation with some like randomly withholding 10% of the data. So that had pretty much no effect if it was random. We also did a spatial cross-validation, like withholding for specific regions, and that did like degrade the model performance. So depending on the case, so we had 4 different regression models for our 4 different cases. So on average, the reduction in R squared was about like 0.05 or something. It ranged from 0.03 to 0.09, the reduction in R squared by the spatial cross-validation.
Reduction compared to when you weren't doing cross-validation?
Right, yeah, sorry.
An improvement over like the base model without adjustment, right?
So that's a reduction compared to using the full data set. Yeah, thank you for the clarification.
It can only get worse if you pull out some observations, right?
Sure.
But I assume even you're saying it went down just a little bit, so it's still an improvement over the base model.
Yes, yeah.
Gotcha. Okay, great. Any additional questions?
No, not at this time, not for Nash.
Great, thank you so much, Nash. Our final presenter is Pradeepa Vanam from Ramble, who presented on an enhancement and testing of hemispheric CAMX. Is Pradeepa here?
She is.
I'll give you the stage, Pradeepa.
Yeah, sorry, I'm on mute. Hello, everyone, and thank you, CMAS, for giving us this opportunity to present our work in this platform. Last year, we presented hemispheric CAMAX for the first time, and we showed how the hemispheric source apportionment can be transferred to a regional domain into boundary conditions. And this year presentation is a follow-up work of what we did last year, and where we evaluated and implemented the option of using satellite data as a top boundary condition, and also tested few sensitivities such as changing the vertical resolution, improving it in the upper troposphere, and also changing some of the world physics options such as subgrid convection to just see how the model is performing. And we provided those details and results in the presentation. And lastly, we evaluated HCAMAX with HCMAC and Geoschem using both ozone sondes and surface observations. And we selected a few sites throughout the North America in subgroups such as Europe, US, Asia, and some sites in oceans. Yeah, so, and those results are also included in my presentation. So yeah, that's all I have for the quick overview. Yeah.
Well, very good overview. Thank you so much. So now that was our last presenter. So if there's a specific question for Pradeepa, or we can open it up more broadly to all of our 16 panelists.
There is one, most of the questions are already answered in the Q&A by the panelists, but I have a follow-up for Mike, which I think is a follow-up from the previous question of the PM 2.5. And it says, will you consider data simulation to adjust the initial conditions and improve that underperformance?
And is my mic on this time?
Yeah.
Excellent. Yes, we, that is part of our development plan to include chemical data simulation. We've started that in our global model now, where we are making North American ultraviolet forecasts, and we are assimilating ozone from, I think, 6 satellites. So that's our first toe in the water in terms of chemical data simulation.
Thank you, Mike. I don't have anything else in the Q&A. We're good with time. Any panelists want to ask another panelist a question? That's also an option. So I think this is it. Kristen, we're good with time. This was great. We have, so our panelists know as well, and everybody, we have 157 participants at this time. We want to thank everybody for their great work.
Marina, just real quick, did Changxi ever?
No.
Okay, sorry. Just didn't want to end up skipping him. Thanks.
Yeah, no, that was a good question. No, he didn't show up, unfortunately. So I think it's wrap up time. Thank you, everybody. Enjoy the rest of your day. We'll see you tomorrow at another session.
Thanks, everyone.